We're going to pick up where we left off on Chapter 6. In the gas laws, we did the ideal gas law, I believe, Bibner.
I think we got the combined gas laws.
We did the ideal gas law, did we not? PV equals NRT.
Nope, let's start that way. We just finished up combined gas laws, it's in 26.
Okay.
I'm not mistaken. You just give us Avogadro's law.
Avogadro's law, okay. From Avogadro's law, we can then do what's called the ideal gas law. PV equals nRT. P is pressure, V is volume, N is the number of moles, R is called the universal gas constant. What we're going to use is R is equal to 0.0821 liters times atmosphere divided by moles times Kelvin. Those are the units for R. R also can have some other units. You're going to use millimeters of mercury and Kelvin. So I prefer to stick with this and change everything else into the units we need. And then you have to remember one constant. So, looking at this problem, how many moles of gas are contained in a typical human breath that takes in 25 liters of air at 1 atmosphere pressure and 37 degrees C? Again, when you look at a problem, see what information you're given. You're given pressure, you're given volume, and you're given temperature. You want to know moles. If you're asked for moles or mass, you're going to use the ideal gas law. Remember, the ideal gas law is EV is equal to nRT. We look at R, universal gas constant, 0.821 liters times atmospheres divided by moles times the temperature, K, tells us what our units have to be for everything else. So pressure has to be an atmosphere. So pressure is already an atmosphere. So I can put the 1.0 here, ATM. The volume has to be in liters, and we have liters, so we're fine here, 0.5 liters. N is what we're looking for. T has to be in Kelvin. We're given in Celsius. So to make it Kelvin, I got to do what? Plus 273. 310 Kelvin. So I put 310 Kelvin there. So if I'm going to solve for N, I get 1.0 ATM times 0.50 liters divided by 0.0821 liters atmosphere per mole K times 310K. If I do that, N comes out to be, calculator out here, a quick calculation, 0.5 divided by 0.0821 divided by 0.02 moles. Let's see, significant figures. I need two significant figures, 0.020 moles. Okay, here's our conversions. .02 moles.
What page is it?
Question? I'm not sure what page that's on.
Do you divide by 310?
Yes. So N, if I solve for N in this equation, N is equal to PV divided by RT.
Okay.
So RT is on the bottom.
Got
RT.
What is 310?
That was the temperature in Kelvin. It gave us 37. We had to change it to Kelvin. The important thing to remember is you always have to have the proper units. Right? If, for example, I was given 700 millimeters of mercury as the pressure, I need the pressure in atmosphere. So I have to convert millimeters of mercury to atmosphere. How do I do that? 1 atmosphere is how many millimeters of mercury? 760. So it's just a conversion times 1 atmosphere over for 760 millimeters of mercury. If I do that, I think it comes out to be 0.92 atmosphere. Remember, your units have to cancel. So just don't blindly stick numbers into the equation. You won't get the right answer. Questions? Okay, if you look at the human lungs, the average total volume is about 1/2 liter. Average lung capacity is 4 to 6 liters. So your lungs contain about 1,500 miles of airways that have a surface area of about the size of a tennis court. So it's very efficient at absorbing oxygen. Also anything else. A lot of drugs can be given through your lungs. You know, people who have asthma, they take asthma inhalers, and people who use other forms of drugs, and they'll sniff it because it gets in there, it gets absorbed very quickly through your lungs. The last of the idea of the gas laws is Dalton's law of partial pressures. His law states that the total pressure of a gas mixture is the sum of the partial pressures of its components. So if we have a mixture of 3 gases, A, B, and C, and each have their partial pressure, the pressure of the mixture is just the sum of the 3 pressures. So if I have, let's say, helium, argon, and neon come together, the partial pressure of helium is 1.0 atmosphere. The partial pressure of argon is 1.5 atmosphere. And the partial pressure of neon is 2.0 atmospheres. What's the pressure of the mixture? 4.5. Pressure of the mixture is 4.5 atmosphere.
How do you know what the partial pressure is?
I just told you. I just
The sum of all 3 is
It's just the sum of all 3 is the mixture.
No, I know the mixture, I'm saying individually, how did you know what?
I've made up numbers. you would be given numbers. Now, if I gave you the total mixture pressure and 2 out of the 3 partial pressures, you should be able to find the third one.
Instead of you gave 1 total and 2
If I gave you the total and 2 of the 3, you should be able to find the third one. You just subtract 2 partials from the total. And that applies whether you have 2 gases, 3, 4, 5, 16 gases. So Dalton's law of partial pressures is fairly simple. So a sample of exhaled air contains 4 gases with the following partial pressures: nitrogen, 563 millimeters of mercury; oxygen, 118 millimeters of mercury; carbon dioxide, 30 millimeters of mercury; and water vapor, 50 millimeters of mercury. What's the total pressure of the sample? Okay, so the total is the sum of all the partials. Turns out the total pressure is 761 millimeters of mercury.
So we can keep it in millimeters of mercury?
In this case,
It doesn't matter.
doesn't matter, but all the units have to be the same.
Okay.
In this case, they were all in millimeters of mercury.
So one of them would be in,
Atmospheres,
Yeah.
you'd have to
And you would,
change
the other two. Or,
Yeah.
Or verse, whichever.
whichever.
Okay.
Now, if they ask you for the answer in atmospheres, you'd have to do this calculation and convert this to atmospheres. So this is 761 millimeters of mercury. Does that make sense? Okay, what is external air pressure at sea level? One what?
ATM.
1 atmosphere. Which is how many millimeters of mercury? 760. So this is what, greater or lower? It's greater. So what kind of air is this? What's it say? What kind of air?
Exhale.
Exhaled air. So for it to exhale, the pressure side of your lungs has to be greater. So is this greater? Yeah. So it makes sense. This mixture inside your lungs has 761 millimeters of mercury of pressure. So when you open your mouth, it comes out. For your nose. We're going to talk about, in this chapter, the ozone layer, ozone, O3. It's formed in the upper atmosphere, the reaction of oxygen molecules with oxygen atoms. So ozone acts as a shield that protects the Earth by absorbing destructive UV radiation. What's been happening is chlorofluorocarbons, CFCs, which are used in refrigerants, those are all your major refrigerants, used to be used in aerosol sprays, destroy the ozone in the upper atmosphere. So that allows more UV energy to enter, which is partially responsible for some of the global climate change. CO2 is a greenhouse gas because it absorbs thermal energy that normally radiates from the Earth's surface. So it may contribute to an increase in the average temperature of the Earth's atmosphere, and we call it global warming. So CO2 emissions have been going up over the years. And you can the greenhouse effect, you can see that when you go out, like today, it may be 54 degrees, you go out, sun shining, you get in your car is hot. It's because the UV energy goes in through the glass, hits your upholstery or whatever's in there, gets radiated out at a different wavelength that can't get back through the glass, so that it stays trapped in your car. So that's called the greenhouse effect. And that is chapter 6.